This is an informational lecture about how real-time PCR works. We've previously talked about regular PCR, and I'd explained how PCR works in that you have a template and you denature the template, you anneal various primers to it, and you use Taq polymerase to extend and make then 2 copies of the template. It can go through another cycle, and then you have 4 copies of the template, and total you can have 30 to 40 cycles. And this traditional PCR is also known as endpoint PCR, because when you're doing this, you usually run a sample on a gel and you just say, okay, at the end of all these 30 to 40 reactions, what do we see on the gel? So what happens is, unlike real-time PCR, which allows quantification in an actual real-time uh, uh, measurement as the template is doubling in the exponential phase, the endpoint analysis is based on the end or the plateau phase of the amplification. So if we were to look at this on a theoretical basis, we'd say every cycle the amount of DNA is doubling until you run out of either primers, or your enzyme goes bad from being raised to a high temperature, or something causes the reaction to stop. You run out of nucleotides or something like that. And if we were measuring this in a piece of equipment, there would be a level below which you would not be able to adequately see anything on a gel or an instrumentation because you simply did not have enough copies. But then in the exponential phase, at a certain point, it would cross a threshold, and then you would be able to start actively measuring the amount of PCR in your sample. But then it runs out of steam, and in an endpoint PCR, this is the point at which you're measuring it right here, not while it's actively growing. So one of the problems with this, if you take a series of 10-fold dilutions, so each of these has 10 times less DNA than the rest, you would expect that this one would come to a certain level and plateau first, and then this one would come to the next level and plateau second, etc. But you can see in real life, when you're measuring the end point of all these, something is possible which actually has more DNA in it. It appears at the end to have less DNA than something which actually had 10 times less amount of DNA, but at the end appears to have a higher amount. So in an effort to maybe be able to more adequately explain how things are moving, and also not wanting to wait till the very end of the reaction, because remember, the reaction takes time, and then you have to load it in a gel and wait for the gel to run and wait for the gel to stain and things like that. People started using this technique called real-time PCR so that things could be measured in real time, and it's a lot more accurate if you measure them in the exponential phase. You tend to get much more accurate results than waiting till the end point to be able to do the measurement. So there's several different techniques that are used in this real-time PCR methodology. And the first is a chemical called cybergreen. So cybergreen binds to double-stranded DNA. How you use it, it's very easy to use. You just put like a microliter or 2 of this extra cybergreen chemical into your PCR reaction, and the cybergreen will intercalate into double-stranded DNA, much in the same way that ethidium bromide would intercalate into double-stranded DNA. So when the DNA is denatured, it's not going to intercalate into the DNA, and as the primer anneals to the DNA and the polymerase starts elongating the primer, more double-stranded DNA is made. It intercalates into the double-stranded DNA, and while it's in the double-stranded DNA, it's actually fluorescing. So when it's by itself, it's not going to fluoresce, and as soon as it it's in the presence of double-stranded DNA, it is fluorescing. So basically, as you get more and more double-stranded DNA, you get greater and greater amounts of fluorescence from the cybergreen. So it's a way in real time of measuring how much double-stranded DNA you have in your reaction. Now, there are some advantages and disadvantages to using cybergreen. So one of the advantages is it's very inexpensive. It's just a chemical that's made up. The companies make a lot of it, and it's very easy to use. You don't have to design any specific primers. You don't have to optimize, where your probes are going to bind or anything like that. You just boom, like you're adding in your nucleotides, you're adding in your primers, you're adding in your DNA. You just add in a little bit of cybergreen, and it's very sensitive. So the more of the fluorescence you have, the greater the double-stranded DNA you have. But there is also some disadvantages that come with it. It's going to bind to any double-stranded DNA. So this includes something called primer dimers. So if you don't design your primers that are going to bind to DNA correctly, you can have the primers binding to themselves and amplifying each other. And so you'll have a large amount of double-stranded DNA, but it won't represent your target DNA that you're trying to amplify. It will only represent, the primers that are binding to themselves and making these double-stranded DNA short fragments. And it will also bind to any non-specific reaction products. So remember, we've talked about the need for hot start in PCR. And so the need for hot start is because you can get non-specific reaction products happening. So cybergreen is also going to be binding to those non-specific reaction products. It's difficult to use in multiplexing. So if you want to amplify more than one target sequence at a time, you can try to do that with cybergreen. And as long as they're maybe very different in size, for example, you can tell the difference. And I'll be talking at the end of this lecture how you can tell the difference. But if you get too many things at one time, you really can't tell the difference through just based on like the size that they are. So you can maybe amplify 2, maybe 3 different things at a time. But once you get beyond that, cybergreen is completely impractical for use. And at very high concentrations, cybergreen can actually inhibit the PCR reaction. So you do have to be very careful in how you use it. Now, another methodology that was developed was TACMAN. And how TACMAN works is there's an extra probe that is designed, and that probe is designed to bind to one of your target DNA sequences. And on the end of the probe, there's both what's called a reporter and a quencher fluorescent molecule. So what happens is when you want to know whether the reporter and the quencher molecules are within a certain space of one another, you hit it with a particular wavelength of light. So when you hit that reporter with a particular wavelength of light, it transfers the energy to the quencher molecule, and you don't get any resulting wavelengths of light put out. So there's a reporter and a quencher molecule that are attached to this little DNA probe that's also going to be binding to the target. So remember, this is your long 2 strands of DNA that you want to amplify. Here's one primer. Here's another primer and this is going to be the regular type of PCR that we talked about. But in TACMAN, you have this extra little third reporter molecule that will undergo from the reporter to the quencher, fluorescence, resonance, energy transfer, or FRET. So when the reporter is within a certain distance of the quencher, the reporter's hit by like a querying wavelength of light, transfers that energy to the quencher, and no answering a wavelength of light is then put out. But if the reporter and the quencher are not within a certain distance of one another, this fret does not happen. And so then when the reporter is hit by a particular wavelength of light, then there's an answering wavelength that it is put out, because that energy transfer cannot happen because it's not close enough to the quencher molecule. So what circumstances does this happen in? Well, TACMAN uses a particular kind of polymerase. It uses a TACMAN polymerase, and that TACMAN polymerase has 5' to 3' exonuclease activity. So this exonuclease activity means that as this polymerase is extending in a 5' to 3' manner, it encounters this extra primer that's bound to the DNA. And when it encounters this, it does not just nudge it away. It actually, because it has 5' to 3' exonuclease ability, it actually cleaves off this DNA. It cuts this DNA into short little pieces. And as it starts cutting this DNA into short little pieces, this separates the reporter and quencher molecules one from another. And so then you don't have the fret happening. And this is a way of saying, okay, so now every time you have amplified this DNA, some of this reporter and quencher are going to be separated. So you're going to have higher and higher levels of this fluorescence from this reporter molecule. So as the TACMAN polymerase completes its journey across the DNA in a 5' to 3' manner, it's basically completely chewed up this probe. And then, of course, at the next round of amplification, you again, so you have 2 copies of DNA, and each one again will separate, just like you see here, and each one will have a primer bind to them, and this whole cycle will begin again. So some of it is still chewed up, but you have others that are still intact. So and you can have quite a bit that's still intact. So as each round of replication completes itself, you're going to have more and more reporter separated from quencher, so you're going to have higher and higher levels of fluorescent activity. Now, another different methodology, because remember, each of these companies comes up with their own methodology, and they're going to patent it, so nobody else can use exactly the same techniques. So molecular beacons is another technique that a different company came up with to answer this problem of real-time PCR. And rather than having the reporter and the quencher molecules far apart from each other, this uses that same fluorescence resonance energy transfer, the FRET idea, but now the reporter and the quencher molecule have to be very, very close to each other to have that happen. And so when it's linearized, you'd have this portion of it, and then you'd have part of it binding to the DNA. So this is going to be able to bind to the DNA. And then in the 3' manner, this would be where the quencher is. So to show you what that looks like, it's going to look like this. So you would have that middle part binding to specific nucleotides and a reporter and a quencher molecule. But now the difference is the reporter and the quencher are separated by a greater amount of distance, and so when it's actually binding to the DNA, the reporter is active and saying, yes, there's a bunch down here. So in the molecular beacons methodology, you're not actually using something which is going to degrade the DNA. Instead, the polymerase does not have a 5' to 3' exonuclease function on it. So as the primer is extended, it's simply nudging it away. And when it nudges it away, it goes back to this form right here, and the fluorophore and the quencher are close to each other, and the amount of radiation from the fluorophore, the amount of fluorescence from the fluorophore then decreases. So in this type of methodology, during the denaturation step and the annealing is when you have the probe being able to bind to the DNA, and then when it's double-stranded, when it's finished replication, then you have it not fluorescing at all. So you put a lot of this into your PCR reaction, and as you are making more and more of it during the denaturation and annealing phase, you have more and more target for it to bind to, so that you have more and more fluorescence that you see. And so that's how you're measuring it in the particular instrumentation. So you have an instrument, and the instrument needs to be told what type of methodology you're using, so it knows whether to be measuring the fluorescence at the annealing step, for example, or to be measuring the fluorescence at the end of the extension step, because of the differing methodologies for each one. So, how you can tell if you are doing multiplexing on something, how you can tell, let me go back here, is you can have a set of different reporter and quencher sets. So if you need to do multiplexing, say you want to amplify 20 different PCR reactions all at the same time, you can have different reporter and quencher sets. And this will work for either the molecular beacons or the TACMAN methodology. By having these different reporter and quencher sets, you can do multiplexing. You can be measuring a lot of things at the same time. If you don't have all of these, as in cyber green, for example, how you would have to measure fluorescence in cyber green is you have to say, let's do a melting curve of the DNA. So this is how much the fluorescence is changing as you increase the temperature of the reaction. So if you had cyber green, for example, and you wanted to do multiplexing with cyber green, say you wanted to have one or two different things amplified at the same time. And remember, you can't do too many with cyber green. You'd have to know what the melting temperature is for each one of your target sequences. And as you increase the temperature at a certain point with cyber green, all of a sudden the DNA is going to become single-stranded again. And as the DNA becomes single-stranded with cyber green, now the fluorescent molecule leaves the double-stranded DNA and it's no longer fluorescing. So you see a big change in fluorescence. So this graph is change in fluorescence right here. So if you have some primer dimers, for example, in cyber green, you can actually tell that you've had non-target sequences. So if this is your target sequence right here, you can get a denaturation of your primer dimers, because they're going to have a different melting temperature, because they're either going to be shorter, they're going to be a slightly different sequence. If you have non-specific reactions that are occurring, they're also going to have a potentially different melting temperature than your ideal target here. And so what you will see is you'll see this little extra bump as your primer dimers are starting to melt, and you'll compare this to, okay, well, I've gotten rid of some primer dimers, but here is still my overall, activity of fluorescence. And then you can go ahead and be measuring that in terms of, let's go back to this one. You can go ahead and be measuring that in terms of, how much overall fluorescence is there in this particular reaction compared with how much DNA there is. So this is a basic idea of how real-time PCR works.